All right, so in part A, we were just graphing a single linear inequality and ultimately graphing its shaded region, that representing the solution. Now what we're going to do in part B is we're going to graph systems of linear equations. So this is just going to contain two or more linear inequalities. So what we have to do is graph the lines accordingly, shade accordingly, and then our solution set, our shaded region S, is whatever's going to be shared. So whatever's overlapping, that's going to represent our solution in these types of problems. So you could have a bounded situation, which would be one that you could circle. If that's possible, it's bounded. If it's not possible to be enclosed by a circle, then it's going to be unbounded. All right, let's look at a couple of examples. Example number 1. We are to determine graphically the solution set for each system of inequalities and indicate whether the solution set is bounded or unbounded. Okay, so I'm going to start this particular problem in the same way I began the last example. And so what I'm going to do is determine the intercepts of both of these linear equations, if they were just equations. So in this first one, negative 4x minus y is less than or equal to negative 16. The x-intercept would be what? The x-intercept would be what? That's when we let y be equal to 0, and then we solve for x. So our x-intercept would be 4, and it'd be the ordered pair 4, 0. Our y-intercept would be when x is 0. So in this case, in the first equation, when x is 0, y would have to be what? Good, 16. Okay, in the second equation, if I were to think of it as an equation, the x-intercept would be what? Again, let y equal 0, and x would have to be 20. So 20, 0 would be my x-intercept there. And then the y-intercept would be determined by letting, again, x be equal to 0. And so y would be what? It would be 4. All right, so what I'm going to do now is plot these points on my coordinate plane system, and then we'll talk about what to do after we've accomplished that. Okay, so I've plotted my points on my coordinate plane system. I went ahead and made every square unit equal to 2 units. So at this point, I'm going to check my inequality symbols. They're both, they both contain the or equal to component. So that means I'm going to use a solid line. So just do the best you can to sketch this out here. Let's see. Again, a straight edge would be nice, but it is what it is. I'm actually going to turn my paper here for this one. Let's see. And this actually kind of goes through my point. That's not the best, but kind of look like that. All right. So here are my 2 lines. What I'm going to do now is come up with a test point so I know which way to shade. All right, so my test point is going to be 0, 0, because 0, 0 is a point that is not on either of the 2 lines. So let's go ahead and test 0, 0 into the first linear inequality. So if x and y are both zeros, you would have 0 is less than or equal to negative 16. All right, is 0 less than or equal to negative 16? No. So because the answer is no, you go to your coordinate plane system, and you're going to shade everywhere that is really the half plane that is not including the 0. All right? Okay. Moving on to the next linear inequality. Same thing. Again, 0, 0 is not a point on this line, so let's use it to test with respect to this inequality. So 0, 0. Is 0 greater than or equal to 20? No, 0 is not greater than or equal to 20. So therefore, we're not going to shade the region that contains 0, 0. We're going to shade the other region. All right, this half plane right here. All right. So, do you see where you're having an overlap occur? Right in this area here. This would be overlapping all here, all here. okay? WebAssign is going to allow you to do this neater than what I'm showing you, but this is representative of the solution region S, okay? One more thing we should be able to do here, and that is we should be able to do this. Hope you're listening. You should be able to determine all of your points of intersection. So we have to figure out this point right there, okay? So let's see how we're going to do that. So to determine this point of intersection, we're going to set up a system of linear equations and determine that intersection point. So one thing we can do in this particular one is multiply the second equation by 4. And so we'd end up with this. We'd end up with negative 4x minus y equals negative 16, still on top. And on the bottom, we ended up with the positive 4x plus 20y is equal to 80. All right, and we're now going to add these two equations together, and that's going to give us what? A 19y equaling 64. So now we know that y is equal to what? Well, y is going to be equal to 64 over 19, okay? And remember what to do at this point. Once you have one of the coordinates established, you could plug it in to either one of the original equations, all right, to come up with the corresponding x value. So if I use this equation right here, I replace this y with 64 over 19, I end up solving for x, and I get x equals 60 over 19. All right, so now at this point, all you have to do is label this point as what we just came up with, which is 60 over 19, and then 64 over 19 for y. And this should be what? Let's see, 60 over 19 is about 3.2. And yeah, this is 2, it's between 2 and 4, it's pretty close, about 3.2. And this is a little bit higher up, so didn't do a real bad job of graphing these two lines freehand. So anyway, the last thing we have to do is what? We have to determine if this is bounded or unbounded. Well, this is unbounded, okay? This thing goes on forever up and to the right, okay? So it would be impossible to put a circle around this because this is going to go forever up and to the right. Therefore, because that is true, it is an unbounded solution. Moving on to example number 2.